Thanks, Jeff. Hi, I'm Attila, and I'm the lead developer of Intel OpenImage Denoise, which aims to make high-quality and high-performance denoising as accessible as possible. In this talk, I'll present the library's past, present, which is currently at version 2, and also a little bit of its future as well. So OpenImage Denoise is an AI-based denoising library which is primarily targeting content creation workflows, specifically final frame rendering and real-time previews as well. Additionally, it also has dedicated support for bakelite maps. It has a minimalistic C API and C++ wrapper API as well, which makes the integration of the library quite easy. The library is cross-platform, supporting all the major operating systems that are being used in rendering nowadays, and it also has cross-vendor hardware support, running on x86 and ARM CPUs, and GPUs from Intel, NVIDIA, AMD, and Apple. And all this is available as open source under the Apache 2.0 license on GitHub. Let's see a quick example of what OpenImage Denoise does. Here's a noisy path-traced image with 128 samples per pixel. Not a lot, but we can see the difference easier this way. And this is the denoise output. It's not quite as high quality as the ground truth, but it gets close. But how close? Let's see. On the right side, we have the ground truth, for which we had to render more than 200,000 samples per pixel to avoid any kind of visible noise. That's a lot of samples. Even if we will want to render in practice more than just 128 samples to get a better denoise result, it's obvious that OpenImage Denoise can reduce rendering time substantially. So how can results like these be achieved using the library? It's quite straightforward. All we need to do is just to pass an HDR or LDR color buffer of the image to the library, and optionally we can also have some auxiliary feature buffers as well. Currently albedo and normal buffers are supported to get the best image quality. These are processed by the library using a neural network, as we'll see soon, and the output is then returned in another buffer. That's basically it in a nutshell. Since its release, OpenImage Denoise has been integrated into several well-known rendering applications and game engines as well. For example, it has become the default denoiser in Blender. It's available in Autodesk Arnold, most Chaos Group products, Houdini, DreamWorks' Moonray production renderer, Unreal Engine, Unity, and several other products as well. It gained wide adoption in the movie industry as well, for which it was recently recognized with a Cytec Oscar. And the first movie that actually used OpenImage Denoise was The Addams Family 2. And Cinesite was one of the major early studio adopters of the library for this. Since then, it has been used in many other films as well. Here are just a couple of examples. And multiple studios made OpenImage Denoise part of their default workflows. So how long was the journey to get to these kinds of results? The library was released about 6 years ago. Many of the key features were introduced only later, progressively. For example, the training toolkit, pre-filtering, and GPU support. It's currently at version 2.3.3, which was released just a couple of months ago. So let's dive a little bit deeper into the major milestones of the library. The first version was a CPU-only denoiser, which laid the foundations of the library, most importantly, the denoising algorithm and the API. First, this is the neural network architecture that the library uses. It's a quite standard unit doing direct prediction, which nowadays isn't considered state-of-the-art, but as always, the implementation details matter a lot. This method still performs surprisingly well, delivering great image quality and fast performance, especially if advanced optimizations like layer fusions are applied, which OpenImage Denoise does in some of its backends. Using FP16 as the inference data type would be sufficient, but since most CPUs support only FP32, that was our choice here. But denoising isn't just applying a unit to the input buffers. It's a bit more than that. To get the best image quality, the image is filtered in approximately perceptual uniform color space. If the image has low dynamic range, it's fairly simple. We just apply the sRGB transfer function. But for HDR images, we need something better. And we opted for an encoding called PU, standing for perceptual uniform, which handles extremely high brightnesses as well. But to get the most out of this encoding, we should know how the user-provided HDR values map to physical units of brightness. The renderer might know this exact mapping, in which case it should pass this information to the denoiser. Otherwise, the best we can do is just guessing by incorporating an auto-exposure step. But this actually works really well in most cases. To get the best possible quality, OpenImage Denoise introduced a technique called pre-filtering, which I mentioned before, which can help a lot when not just the color buffer, but also the auxiliary features are noisy as well. This typically happens for lower sample counts, but it's not uncommon for relatively high sample counts either, especially if there's depth of field or motion blur in the image. In such cases, the denoising network can have a hard time preserving the finest details, even if it was trained with noisy auxiliary features. The solution the library offers is first denoising the auxiliary features with dedicated models, and then denoise the main feature, which is typical the color, using these clean auxiliary buffers. We've discovered that it's important to denoise the main feature using a model which was trained with clean auxiliary features to preserve as much detail as possible. Pre-filtering can be skipped if we know for sure that these auxiliary features are noise-free, which can be communicated to the library through a filter parameter. This way, the right model will be picked to get the best quality. Let's see some results when using pre-filtering. So first, here's the noisy input color buffer. And here are the auxiliary buffers, albedo and normal. If you look closely, we can see that some areas in the albedo buffer are somewhat noisy, as I highlighted. The problem really is that this noise in these auxiliary buffers can sometimes leak into the final denoise output, which can be quite distracting. However, this can be fixed if we pre-filter the albedo and normal buffers. And this way, not only just the residual noise that we've seen is gone, but many areas in the image have a lot more detail. We need to look a bit closer to see the differences. Here we can see that there's a lot more detail preserved for the surface of this wall, which you can see, and the noise in the reflections from the lampshade at the top is also much better removed. Overall, the quality improvement is quite noticeable, which is why pre-filtering or just flagging the auxiliary buffers as clean is highly recommended when denoising final frames. I want to briefly mention the lightmap denoising feature as well, which was introduced later. The same network architecture is used as for regular images. That's perfectly fine, does the job well. But we found out that to achieve acceptable quality, we had to actually train new models specifically for light maps. And we have two variants, two models for two different kinds of light maps that we support. We support HDR light maps and normalized directional light maps as well, for example, spherical harmonics light maps. In addition to the high image quality, another key focus of the library is the ease of use and integration. Let's take a quick look at the API through this example. This is all it takes, what you can see here, to denoise an image using the library. First, we initialize the denoising device, letting the library pick the fastest available one, which can be a CPU, or since version 2 of the library, it can be a GPU as well. Then we allocate buffers for the input and output images in device memory. We then create our filter and set its parameters. Of course, we need to initialize the input buffers at some point, and probably the easiest way to do that is to just do it through pointers that we get to the buffer data. This actually works regardless of whether we have CPU or GPU buffers. The application doesn't even need to know, because the library, by default, allocates all buffers in unified shared memory, or sometimes also called managed memory, which means that the pointers work on both the host and the device. Finally, we just need to execute our filter, which was set up, and then at the end, we clean up the resources that we allocated. A critical part of any neural denoiser is the training data set, which has a profound impact on the image quality. The models that ship with OpenImage denoise were trained on sets of noisy and ground truth images, which were rendered with a custom Intel Embry-based path tracer. The dataset contains images of just 11 scenes, actually, and multiple images were rendered for each scene, though. And these images have completely random camera views, materials, and lights as well, which were generated fully automatically. And each of them were rendered at every power of 2 samples per pixel, up to 128K or even more samples, this way covering the full range of noise levels that the library might encounter during usage. The rendering resolution was quite low to capture a lot of detail per pixel to actually make these images more challenging to denoise. In total, there are about 35,000 of images in the dataset. Although this dataset works quite well with most renderers and scene times, there's still room for improvement. The library ships with a PyTorch-based training toolkit, which can be used to train denoising models using custom user-provided datasets. Rendering such datasets requires a lot of resources, which not every user can afford, but for example, studios can, who are able to optimize the denoiser for their particular needs, their own renderer, style, their assets, which means that the image quality can be maximized this way. And these user-trained models can be quite easily loaded at runtime through the API or can even be built into the library. We've now arrived at the next milestone of the library, the current version, version 2, and the main focus of which was adding GPU support, elevating the performance to a whole new level. Support was added not just for Intel GPUs, though, both discrete and integrated, but for all other major vendors as well, NVIDIA, AMD, and Apple too. But the biggest challenge was figuring out how to achieve the best inference performance on all these different platforms, while also avoiding to make the library more difficult to use or even make it too bloated. The solution that we found was using the native compute and AI ecosystems of these platforms, which are SYCL for Intel, CUDA for NVIDIA, HIP for AMD, and Metal for Apple GPUs. The API of the library abstracts away most of this complexity, and to a large extent thanks to using unified shared memory. Compute APIs and Metal are of course natively supported, but which many major renderers are based on, but efficient interoperability with Direct 3D and Vulkan is available as well, and it's possible to do efficient zero-copy buffer sharing this way. Adding GPU support finally made real-time performance possible with OpenImage denoise, using the same network architecture and having the same quality as before, for which FP16 as the inference data type is sufficient and widely supported on GPUs. Internally, the library required a major redesign to support so many different compute and graphics APIs at the same time. OpenImage denoise 1 had a trivial monolithic design, this one, where a single binary module contained everything, including the network weights themselves. This had to be changed to modular architecture in version 2, where the CPU and GPU backends are in separate dynamically loaded modules, each having their own library and driver dependencies. For example, dependencies like we're depending on one API in the SYCL device, we're depending on CUDA itself in a CUDA device and Cutlass. We depend on HIP for AMD GPUs and the composable kernel libraries used, and for Metal, we're using Metal performance shaders. But applications still need to link against just the main library at the bottom, exposing mostly the same API as in version 1, and don't need to worry about all this complexity, all these dependencies. It just works. It's just really a detail of how the library was implemented, and actually it was quite a challenge to make it work in a build system even, because as you can see, we have quite a few compilers being used here. In addition to the GPU compilers, we even have ISPC2 for CPUs. Another new feature that OpenImage denoise 2 introduced was a denoising quality parameter to make the library more scalable, which is implemented using network models of different sizes. The existing models have become part of the balanced quality level, and 2 new levels have been added, fast and high quality, offering both faster and higher quality denoising than before as well. Despite these improvements mentioned so far, OpenImage denoise still has some notable limitations. First, the UNet-based direct prediction architecture is starting to show its age. It's getting increasingly difficult to further improve quality, and this method is also prone, unfortunately, to some artifacts like ringing, which is particularly bad in light maps, for example. It's prone to over-blurring in some cases, and some minor color shifting too. The second major limitation, of course, is that the library still supports only denoising individual frames, which means that it isn't temporally coherent, and it doesn't support any kind of upscaling either, which would be quite useful, for example, in real-time use cases. However, I'm now excited to announce that the next major version of Intel OpenImage denoise, version 3, is well under development, and it aims to address these mentioned limitations. Specifically, it will introduce a superior network architecture, and it will add support for both temporal denoising and supersampling. However, please note that since OpenImage denoise 3 hasn't been released yet, some of the following details are still subject to change. First, the library will switch to a new kernel prediction-based denoising method, which is the first major update, actually, to the network architecture since its original release. Under the hood, the method is still based on UNet, but it provides some significant improvements over simple direct prediction. For example, it fixes some of the artifacts and improves detail preservation in some cases. Kernel prediction also enables a feature called composable AOV denoising by being able to reuse the same predicted kernels for multiple AOVs, which is commonly used in production, for example, for movies. And this improves performance and also consistency between these denoise outputs. There's another performance benefit to this, is that with kernel prediction, it's now possible to quantize at least the most expensive part of the denoising network, which is called the feature extractor, without degrading the image quality. We found that int8 to be a good sweet spot in terms of quality, performance, and accelerated hardware support as well. However, filtering is still done in FP16. Here's how the new kernel prediction network looks like. We still have our previous UNet in the top row, but instead of directly producing the denoise output with it, it's just a feature extractor. Per pixel normalized convolution kernel weights are predicted at multiple scales from the extracted features, which can be seen in the middle row. And in the bottom row, we have the filtering network, the least expensive component of the network, which actually denoises the input image using the predicted kernels. Now let's see how this new network performs. Here's a noisy image of the well-known Moana Island scene. This is the output with direct prediction. And finally, this is with the new kernel prediction. The image quality improvement isn't really dramatic, but is noticeable. But we need to zoom in a little bit to see it better. Hopefully, here we can see that kernel prediction does a much better job preserving some fine details in the tree, the leaves, branches. There are 2 variants of kernel prediction shown here. One in the middle, still using FP16, and another one using int8 quantization as well, but there's no visible difference between them. As I mentioned before, one of the most problematic and annoying artifacts that this new network fixes is ringing. And actually, the easiest way to spot this artifact is with very simple scenes like the Cornell box here. But again, to see the difference, let's zoom in a little bit. Take a look at the highlighted regions. With direct prediction, there's some quite strong ringing around the edges, but this is completely gone with kernel prediction. Flat regions are also smoother, but that's even harder to see here. OpenImage denoise 3 will also finally introduce temporal denoising, which is by far the most requested feature. Actually, it will have not just one temporal variant of the new kernel prediction network, but 2, but for different purposes. One of them will be a real-time frame recurrent filter, which will support joint denoising and supersampling using the same network. This will require the previous output frame, backward motion vectors, and depth as additional inputs. And for supersampling, the input will also need to be jittered as well, which is quite standard for these kinds of approaches. And the other temporal filter that will be introduced will be designed specifically for high-quality final frame rendering, which will be able to leverage not just past, but future frames as well, since we typically have them available, requiring both backward and forward motion vectors in this case. Now, all this, OpenImage Denoise 3 is expected to be released toward the end of this year. So it's time to wrap things up. We've seen that Intel OpenImage Denoise is a scalable denoising library which offers solutions for the entire content creation process, ranging from real-time previews to high-quality final frame rendering. It's cross-platform, has cross-vendor hardware support, and it's easy to integrate. And last but not least, it's fully open source, which enables customizations and improvements possible for users. This also makes it suitable not just for production, but research as well. I've just highlighted a couple of references here. And as with most open source projects, contributions are always welcome. We're accepting pull requests. So if you have any improvements to the library that you're able to share with the entire community, then please don't hesitate. We can't wait to see what you're doing with OpenImage Denoise. Thank you very much for your attention. I'm happy to answer any questions you might have.
Thank you so much, Attila. Do we have any questions from the audience? Yeah.
Fantastic talk, Attila. Could you comment a little bit on the bottlenecks? Let's say when you get with new hardware 2x the int8 performance, how much would this speed up the entire process?
Well, I mean, it won't be 2x, of course, because even right now, we have memory bandwidth limits for most architectures, and I expect that even with int8, we would have some memory bandwidth limits, but of course, it will be a bit less, not that as severe. So, and we also need to take into account that not the whole network will be quantized to int8, like we have the filtering network, but it takes like, I don't know, 10% of the total denoising time. So it cannot be really a linear speed up, but I don't really have any exact numbers, but I would say that the reasonable overall speed up could be like 50% or something like that in the ballpark.
Great. Any other questions? All right.
Yeah, thanks for the talk. For the cross-vendor support, I'm wondering, do you have a plan to support Vulkan as its backend?
That's a very good question. So at the moment, for OpenImage Denoise 3, this isn't being planned, but it's not quite as important, I would say, since Vulkan interoperability is quite good. I mean, it doesn't really have every components of the interoperability yet. So, for example, you can share buffers, but you cannot share semaphores, for example, which can be a bit problematic because then there's some additional overhead when synchronizing the CPU and GPU parts. But initially, in OpenImage Denoise 3, this will be addressed by adding support for semaphore sharing as well. So the overhead of using interop with Vulkan should be even less than it was before. So it's not quite Vulkan, but it should still work quite well, I would say. I mean, supporting Vulkan has its own challenges because using the same code base for all these different platforms is, of course, possible, as we've seen with graphics very often. But with AI, it's a bit trickier. I mean, there are new tools there, but it's still, there are so many differences between the architectures that it's unlikely that even with Vulkan, you could use just the same code for all the different vendors and expect to get the best quality out of them. The advantage of using these different compute APIs was that we could use the native AI acceleration libraries that are based on these frameworks, so we can really use the best possible primitives to do the inference instead of doing everything manually, which we would need to do with Vulkan. So these are basically the challenges of adding Vulkan as directly as a backend. So it's not excluded as an option, but not directly planned for the moment.
Thank you.
Great. Do we have any other questions? All right.
Great talk. I wanted to ask you if have you considered or maybe consider in future to other architecture rather than UNet, like this modern, like transformer-based
Yes,
attention mechanism?
absolutely. So essentially, the plans that I've shown here are really for the initial version of OpenImage Denoise 3. So this will come next because this is already being developed. But yes, we're also looking into other network architectures as well. I mean, this is a lengthy process because in research, it's one thing to pick a network architecture. I mean, many variants of kernel prediction have been published, but what we found is that when you're actually trying to use it in a production context, then it doesn't quite always work as it's advertised, I would say. That it sometimes has some quite shocking or annoying pitfalls which could actually break it completely, like would make it unusable, even though it's promising like on paper, like looking at PSNR, SSIM, but the reality, I mean, is that you cannot really have any kind of metrics like this to just say that, yeah, this is obviously better than the other one. Like this, I'll give you one example that there are some other more advanced kernel prediction architectures than the one I've shown you, but what turned out is that it's also prone to ringing, which defeats one of the purposes, one of the goals of switching to kernel prediction for us is that yes, in PSNR and SSIM, it got better results, but it had the same annoying ringing as before, and we had many problems and complaints because of that. So yes, we will look into other network architectures, but it will take more time than switching to a new architecture in the research community because it needs to be tested for so many different use cases. We have so many different kinds of customers with different kinds of rendering methods, scene types, animated movies, VFX. It takes a lot more time this way, but I'm pretty sure that we won't stay for very long with this architecture. It's just the next step over a longer period of time.
All right, I think we have time for one more. All right.
Great talk. With the light maps, do we supply anything else to maybe help with the seams or any potential problems?
Yes, so seams can happen, that's true. I mean, the biggest problems were the ringing, as I mentioned, that when there's the background and then you have the actual maps, then around the black borders, then we got all these different borders inside the mapped surfaces. That was the biggest problem, and we needed some tricks to alleviate that, but with kernel prediction, this will be gone, hopefully. With seams, we haven't really got any complaints, I think. That's a possibility, but by far the ringing was the biggest complaint that we got from the customers.
Okay, let's thank our speakers one more time.